Good afternoon, everyone, and welcome at our last press conference of the day, which is all about sensor webs. With us are the two conveners of the Earth and Space Science Informatics session about sensors, which will be held on Thursday afternoon, if I'm not mistaken.
That's right.
On the right is Dr. Walter Schmidt from the Finnish Meteorological Institute, and on the left is Dr. Dennis Havlik of the Austrian Institute of Technology, who will assist Dr. Schmidt during the question and answering session. Okay, go ahead, gentlemen.
Yeah, good afternoon, also from my side. And the subject is something which had been developing over the last decades, which someone phrased as the Earth's electronic skin. And now, even if we do not realize it every day, we are supported by millions of monitoring devices from our pocket over household appliances all the way up to space. And without monitoring of our power networks, traffic systems, and all the communication systems, we wouldn't know probably anymore how to survive. But, and this is the big but I want to put here right in front of this presentation, there are the big three question marks. First of all, is the information sufficient? Are we lacking sensors, whatever? Is the information reliable? That is certainly put into doubt quite often by lots of specialists, laymen, the press, politicians. But the last but is, does actually the information reach the relevant decision makers in any useful form? I'll come to these three main questions then at the end and also in the middle. But as you remember, probably just a few weeks ago, we were directly faced with the consequences of what this electronic skin can do for us when the volcano in Iceland ejected its ash clouds all over Europe. And as a consequence, the airplanes were grounded. And then it was said quite often that the only reason for that was that model predictions told that flying over Europe might be dangerous. Actually, what you can see here is what actually happens. So all the time, like you see on the ESA Envisat image, and I just marked the ash cloud you can see on this image here, it was monitored by more than one spacecraft all the time. It was fed down in real time into the networks of the science and observation institutions, was fed into the model predictions that were updated in a couple of hour intervals, and then the information was made available to the aviation authorities directly, and based on that, it was then decided which area might now safe to fly, which might not, and that was changed and discussed a couple of times a day. And in between, and that I put in here in red, there was also verification by ground-based observations, including airplanes. And that is a big problem, for as it turned out that we do not necessarily every time have actually enough ground-based observations to support in situ the remote sensing information. But what's the main point in this slide is that without spaceborne monitoring and the related communication systems, it would be very difficult to cover large uninhabited areas like the oceans or the deserts or jungles. And like in the mid-80s, it could then happen that an airplane drives or flies through an area which should be nice and clean, but actually is covered by an ash cloud and everything just stops, that it didn't come at that point to a major accident was probably more chance than anything else. So lesson learned from that, we have a lot of information, but we always have to have, additionally to remote sensing information, also in situ and ground-based observation devices running to monitor the environment. And as I point out here, crisis management needs always both. So back to the start, the segments of our Earth electronic skin is mainly made out of these four groups. First of all, of course, we have to have sensors, sensor infrastructure, network, either space-based or on ground. And the information gathered there has to be distributed from the sensors itself to services which can deal with them. Then that has to be interpreted, analyzed with a lot of sophisticated tools based on rather advanced sciences, and eventually the hopefully meaningful information has to be presented to the decision makers in a way that they are not just guessing what they are doing, but have some well-founded point. So what's the challenges now? Why are we discussing this now? So let's start with the infrastructure in space and on ground with the sensors. The coverage might be rather difficult, partly very good, as you have seen, partly difficult. The resolution in time and space varies quite a lot, and quite often it's such that actually at that moment when we want to have an observation, it doesn't exist. There was a fault there, or it just happened to be not covered, or a mission was terminated and wasn't replaced by another one. And or the data got lost. And additionally, there might be errors due to many reasons. I'll come to that later. But let's assume we get the data, first of all, from the sensors. And now they are there somewhere. But how do we know where they are, what is actually available, and with what precision, and so on? And this topic had been discussed in several talks and will be discussed certainly more during this week here. And once all these data are gathered, perhaps even at the same location, we have to combine them in order to make as well possible use of them as possible. But unfortunately, quite often they are formatted in a different way, scaled in a different way, described in a different way, and it might be extremely challenging to actually utilize all those different data sources which have been put up mainly with tax money, and quite a lot of them. And finally, once we have results, that doesn't help actually anyone. We need useful and understandable results. And once they exist, we have to find a way to make it available to those who urgently need them. In the case of this volcano ash, that was easy. The meteorological institutes generated the data, and the aviation authorities needed them. That was very straightforward. But in all other cases, quite often I would say the decision makers don't even know that such data could be available. So going back to the current development of these different areas, sensor technology, the major breakthrough steps, I think at the moment at least, are over. There might come new ones in the near future. But what we have here is mainly in space, spectrometric cameras with more and more data generated, high resolution, which could be used for atmosphere monitoring, agriculture, forests, archaeology findings. And with the synthetic aperture radars, excuse me that I use this term, it's just a matter of not a big radar antenna flying there, but it's a computer which makes radar images out of very simple, straightforward radar signals, which are just coming from a simple but long antenna. And the possibilities there are, for instance, looking through ice into the water, thereby measuring very precisely ice thickness, snow thicknesses, ocean levels with respect to the center of the Earth, for instance, and so on. And then going to ground, we have these different polarimetric weather radars, which are just coming. You might have heard about them, that now, in order to prevent further accidents close to airports with planes crashing into swarms of birds, some of these weather radars are reinterpreted with the signals and reconfigured to monitor and spot such birds. So far they had been just scaled away, for we were interested in rain, not in birds. But the signals nevertheless were there. And that is something rather new that was started only a couple of months ago. And then there are laser-based atmospheric pollution monitors and mechanical sensors to monitor volcanic activities. You find some presentations also in the Thursday session, either on the poster or oral. You might want to look at that. Now, once we have this data, we have to do something with it. And this is a general concept of what happens. So here on the left-hand side, you see all the data collected, as I mentioned. On the right-hand side, you see what the public and different aspects of the public would like to see. And in order to make that possible, there are a lot of sub-boxes needed, from translation services via general applications up to special possibilities, making it possible to the various citizens and decision makers to look at the data in a way they understand. At least that's the intention. And we will now mainly then concentrate, as far as network structure is concerned, on this central area. And that's what it roughly looks like. Down here, you have the sensors. They must not necessarily be on ground. They could also be in space, of course. On top of that, you have then some services which collect the data, send them perhaps via cables or via satellites or however to certain collecting areas where they are merged, pre-processed, scaled, put into physical units which make sense, at least to a physicist, and then will be displayed in nice color maps with hopefully some annotation, and eventually might be sent as reports out to authorities which are interested in them, or just end up in a nice scientific publication in a journal, and anything in between. Or people might directly look at it and using this user interface support, whatever that is. User interface just really means you as a user are sitting there doing something and eventually see the data. That might be a rather challenging part. Here on the left-hand side, you see a few implementation examples. For instance, the Sunny part, which implements this structure for certain purposes. I will show a few slides down. Wrote some for air quality monitoring. A completely different area is the next line here. The mouse always vanishes. So for planetary data, and that both are actually funded by the EU, and the idea is in both cases collecting data from very different areas, make them available to different users, and eventually then allow to make either progress in understanding what happens or different use during the decision making. And just in case you are interested, the US has set up this governmental program a couple of years ago called National Spatial Data Infrastructure, which is not something which exists, but something which is built based on a governmental decision, for they realize it has to be done. And that is now slowly implemented for different areas. We heard today one presentation, for instance, about water supply and rain and corresponding databases and to make them available. Now, to the data I mentioned, they are collected from different authorities, partly private institutes. First of all, they are very difficult to find. If you find them, then it might be very difficult to understand. And if you find the information of how to understand them, you still might not be able to really interpret them. So the data provider writes the best as he or he is able a certain description of what to do with the data. Unfortunately, that might not exactly be the description you need for whatever you had in mind with those data. So there was this project T2 developed, which allows actually to tackle this problem, looking at the data once you figured out, perhaps with a year of work, how to utilize the same data for your own purposes, which might be something completely different than the one measuring them had in mind. You could feed it back to the system so that the next one doesn't have to spend another year to do exactly the same thing. Next big question is, which always comes, of course, also from the public, how reliable is actually this information which is produced via these networks? First of all, there's a big systematic problem. As different and rather important areas are not covered for infrastructural reasons, third world areas that simply don't have the means to do that, or for political reasons, it's too dangerous to measure something there. So there might be large areas which are actually not covered, and therefore important factors might be missed. On the other hand, it might also be that the analysis tools are simply too straightforward, that they really miss some important aspect of the data which are still there and might in the future actually be found. What's first of all in fact affected by that are any kind of long-term trend analysis for either resource development, slowly is vanishing as everyone knows, or weather and climate development, where most of the discussion is going on right now. And depending on whom you ask, you always get different answers due to the fact that everyone makes different simplification. Until a couple of years ago, no one used actually the effect of the oceans on the climate due to the fact that it was too complicated, not that the oceans weren't there. On the other hand, you have to ignore certain areas of Africa. You simply don't have any monitoring station there. You can't claim that Africa doesn't contribute to the global climate. But I think rather than going there and get shot, you try to do something to your models. So this one has always to keep in mind that analysis can't be better than the data you actually get. And that also means that any kind of data precision claimed might actually lead to wrong resource estimates due to the fact that you simply guess in the wrong way. Everyone makes intelligent guesses. A very simple thing is you have a weather radar, you are looking at the atmosphere, and you see with the radar it's raining heavily in 100 kilometers distance. Okay, the persons living in 100 kilometers distance realize it's not raining at all. What went wrong? There's something like the curvature of the Earth. So if you look at 100 kilometers, you look actually rather high up. And if it's warm enough, it might be raining up there, but the drops either go to some completely different place due to wind, or they vanish altogether. So that is always to be kept in mind, and the difference is done by modeling. And everyone uses different models and comes to a different weather forecast. So, problems, challenges we have to fight with. Let's have a short look at Spaceborn instruments. You might have heard something about space weather. Sounds always very funny. It just means that the radiation out in space could endanger instruments and the communication links between the satellites and us. But not only that, but not very many people know, it might also reduce the precision of our nice GPS systems, especially in Scandinavia, where I am living. And like this little image tells, the plane is flying there, it thinks it's above Stockholm, but actually it's already a little bit further east. Or the boat is coming to a harbor completely automatically, and if they don't switch their GPS system off and have a look, they might crash against the next wall. Not normally, but if there's something very heavy, like space weather going on, the ionosphere between the satellite and the ground receiving station might look much longer than the little receiver assumes. So that's where these problems come from. Normally you are talking about a couple of meters and only in Scandinavia, but it can happen during solar maximum, which we are slowly approaching, also here further south. Every time you basically see an aurora, if you ever have seen one, that means GPS readings might be unreliable. For that happens only if the ionosphere looks different than the GPS system assumes. Next problem, as I shortly mentioned, related to ground instrumentation. The political situation might be such that you simply don't have any sensors or can't repair them. Or, like this a nice weather station up in northern Finland, it might be actually rather cold, and there might be some interesting side effects we are not going into now. But what I mentioned already, incomplete information in one location can lead to difficulties in the prediction and a completely different area. And therefore, I think the idea of an electronic skin isn't that bad. If you have a skin problem at your leg, you might actually have problems with your brain also, for you would like to walk somewhere and you can't. So it's not actually that bad. Next step, the analysis tools. The main challenge is we need new strategies to cover all this huge amount of data, especially image data, which are coming in more and more. No one can look at all those data. We're talking about terabytes, and that's one with quite a lot of zeros, 12 altogether. And so we need automatic tools which recognize information inside the image data, which can be used then further. And normally here you see a normal analysis flow. You get any kind of data, whatever it is. It has to be smoothed a bit, for normally there are problems, errors, gaps, whatever. And then it's analyzed, put into physical parameters, let's put it that way, like velocities or something. And after that comes the most important step, quite often also forgotten. You never see measurement data. What you really see is data which are fed into a model. Then the model is modified in such a way that it represents the data, and what you see as data are actually the data which were fed into the model. And that's what normally is the result of a measurement. So it's not the data themselves, you can't do anything with them. But what you really normally see is the way how you have to adapt your model that it fits the data, and then you know, provided your model is correct, what is really going on. And therefore, there's always this feedback all the way down to the data, might need correction, and so on. But besides that you need the model, you have to have the information provided, what I mentioned with this metadata. It has to tell you how to use the data. Even such a simple thing, are the data from today or from yesterday? That's not that straightforward as it looks. For everyone might actually have a small glitch. The clock might have jumped or other reasons. So you have to clean up even such a thing like time before you can compare data from different sensors. And my colleague Havlik is actually giving a presentation related to this topic on Thursday. The next big problem also related with the data images is the capacity. We have now very fast machines, and that we need, for we have a huge amount of raw data, image data coming in. And one way to tackle that is using grid computing. So you have lots of different computers all over Europe, for instance. They are connected by very fast links. What quite often is forgotten is it doesn't help if in Graz or here in Wien, in Vienna, there is a big machine which calculates the data for 10 seconds, and the next free slot is in Hamburg. In the meantime, you have to transfer huge amounts of intermediate data results across data links, and that takes ages. So no matter where we look, we always run against the wall. And we have to find more intelligent strategies of how we tackle those these problems, and they are presented here also then in some of the sessions. But the result of that is one has to make a compromise, which means we have a huge amount of data of everything imaginable, and a lot of things you can't even imagine, and only very, very tiny fraction of those will ever be actually published or made known to other people. As an example, this famous ozone hole over the Antarctica wasn't actually discovered by those who measured the data, but by some Indians who went back to the old archives for lack of something better to do, and then went through these old data. No one was interested anymore, and actually found these effects. It could have been found right away if someone had put the effort into it. And now we are getting close to the end here. So as an example for such an integrated structure, which starts with monitoring data, sensor network, and then depending on what we really want to have, then modify the data, combine them, cleans them, eventually make them available to decision makers, shown here. And one could generally call it an infrastructure service. So it puts infrastructure elements together, including modeling, and makes those results available to authorities, researchers, or a layman who is interested in it. So which problems are still open, or can we actually just quit any kind of research? First of all, the already mentioned meta-information gap and the huge amount of data which, like an avalanche, is increasing per day dramatically. And that's related with quality, and due to the fact that there are so many different interpretations of the same data, it relates also to trusting in the results which are taken out of them. And then all the information about how the data were collected and so on has to be managed, not just the data themselves. And that is a huge challenge, which is also tackled in several sessions and different talks and posters during this week. And then eventually the data themselves have to be analyzed and put into a handle form, either films, graphics, images, or plain numbers, depending on what should be done with them. The other part is, I would say, nearly more political and partly even up to the press. First of all, data are collected everywhere, but that doesn't mean that everyone can get hold of them. There might be a conflict between two neighboring countries. They are not talking to one another, let alone exchanging data. Or they might be willing to exchange data, but there is no technical means to actually do that. And most of all, there might even be some physical problems hidden behind the data collection process, which are not completely understood, and which might prevent some of the data analysis to be carried out. And then, of course, such simple things like a network breaks down, you know that from at home, and you have 80% of the data, and the essential 20% are missing, and you can't do anything with the 80% either if those 20% contain these metadata telling you what to do with the rest. So everyone knows that. My colleague is smiling. So So, and this is in my opinion, the most important part which we scientists usually forget. For once we are here, we are happy. We write our publication, very happy if it's published and accepted, and that's the end of it. But how do we make sure that those who actually are paying us, the taxpayers and their representatives, ever get to hear of them? And do they actually know what we are doing? That all the information they are lacking might actually be available. If no one tells them, they certainly will not know. And if they hear about it, it's a question if they get the information in a way that they understand them and can make intelligent decision. So what we are going to do in the next time, first of all, sensor development certainly will continue in the same direction as always. More lightweight, more low power, and application both ground and space, and complementing the existing instrumentation, and therefore then having data sitting, what I know, on some moon close to some other planet, or sitting in Antarctica or wherever, or even close to a traffic crossing with all the poisonous gases. So infrastructure, that's where also this week is concentrating on. Combine different data sources, different models, and make it eventually into an easy-to-use product. And to re-emphasize this once again, this one will be one of the most challenging aspects in the next future, which was also stated by the policy statement of our EGU's president, Mrs. Tuija Pulkkinen, on Monday, telling that really this public relation information policy is very important. And with the move of the EGU secretary over to Munich, concentrating everything there, the EGU is hoping that this will actually be advanced in this direction a bit better than it was in the past. So the last one is just information in case you're interested in what it was I was referring to. And at the end, a little advertisement for the actual sessions related to this press conference on Thursday afternoon, as well the posters in Hall Z, as the oral session in room number 7. Thank you for your attention.
Thank you, Dr. Schmidt, for your presentation. There will be time now to ask questions to Dr. Schmidt and Dr. Havik.
Hi, I'm Liz Callagher from Environmental Research Web. Could you tell us a bit more about how people will be informing decision makers and the press about the tools available? What measures you're taking so far?
Yes, the main intention so far is to increase public relation work and increase also the activity of the EGU press office. But related to that is, of course, also the fact that this task is laid onto all of us. And now, more than ever, every single project where you get any funding from the public always contains a clause where you have to state in which way you want to disseminate this information and the results of that project to the public. So a public outreach part has to be convincingly stated. And if it's not there, no one will actually look at the proposal. Yeah. So in this way, it should be better.
Just to give you one real-world example, I've been leading this integrated project SUNny for the last 4 years. It's just finished. And there we had clear dissemination to several groups of people, including like decision makers. And so during this project, we have organized, I think, 6 or even 8 training sessions, which were partially technical trainings, partially more like high-level explaining of the stuff. Then we had about 9 demonstrations of the pilots. One of them was shown here, this air quality pilots, other were in domain of urban geohazards and bathing water and quality of seashells. Then we had quite a lot of stuff, of course, published just in journals, several things in normal newspapers. I mean, normal newspapers, things everybody reads, like their standard here in Austria. And then at the end of the day, we even published a book which has two parts. First part is a 30-page summary of why and what we did in a project, which is readable for anybody. Well, not anybody, but many, many people in the world, not just, the scientists, will be able to read that and understand what we are doing and why. And it has nice green cover as well. And this is, unfortunately, I was kind of surprised with this because we had problems with communication, so I don't have any books here. But they can be downloaded, and if anybody wants, I could give you a hard copy. Sunny web page is very easily found on Google, so you can download it from there.
Sorry. I'm Sabrina Ria from the French press agency AFP. In the light of what you explained now, how do you assess what happened in Europe with the eruption of the Iceland volcano relating to really the different informations that were gathered and how the public authorities dealt with it?
Okay, yes, I was to some extent involved there working at the Finnish Meteorological Institute, which was the data analyzing authority in Finland. I think one of the problems as far as public relations is concerned, in my opinion, which was made, was that strictly any information every 4 hours, around the clock, was given only to the aviation authorities. And these information were based, as I mentioned, on models correlated with direct satellite observations, plus so-called in situ measurements, especially in Scandinavia. So we, right on Friday, had actually special military aircraft up collecting ash particles from the critical altitudes. And when they came down already after 3 minutes with slight engine damage, the aviation authorities were rather confident that their decision to close the air space was correct. And that kept going for 10 days. So round the clock, every 4 hours, a new estimate based on new data was produced and actually transferred then also to London, for it was decided that they will do the general European-wide dissemination in order not to have clutter and conflict in a discussion. But the information was basically only given to the aviation authorities, and that perhaps caused some of these problems, as I read in one Lufthansa statement claiming that everything was just based on some model assumption of some scientists gone wild in London. So I would say it was actually handled from the technical and scientific side rather well, and still we have to learn very much on the PR side, which I try to point out here during my talk, also partly based on this PR disaster.
Did other countries than Finland actually had planes flying? Because I heard that story from Finland. So, okay, they made the proper measurements, but somewhere else in Europe, was that also done?
No,
I don't know if you know about it.
No, at that time, as far as I know, not. A DLR in Germany did that, but as it always turned out, they had quite a lot of these measurement devices, actually 5 altogether, as far as I know. 4 of them were in repair, and the 5th one was sitting somewhere in a workshop operating, but it took them, I think, 4 days until they had mounted it on a plane. But I think it's not that a big of a disaster. If you have in situ measurements at one location, with which you can verify and tie down your model based on remote sensing. You know pretty well what happens anywhere else. And that's the basic secret, I would say, of remote sensing. You get global coverage where you don't know what it means, up to the moment where you can pinpoint it at least at one point in time and space. And then you are already not too far off. There might be still larger errors depending on how far you get away from this point in time and space, but nevertheless, these models then after that are already rather reliable. And actually, the measurements made by this remote sensing satellites, NVSat especially, it's a huge thing. And one of the big monitoring devices was actually designed in my institute. So we are doing also the analysis. They have actually a rather good handle on what happens all the way down to ground through the whole swath of each orbit. And to speed things up, we had reactivated actually our downlink possibility in northern Finland to a rather high-speed link to get direct input in real time from the satellite and feeding it into our system. So I think it was better than it looked from the outside, but by far not that good as it could have been, in my opinion, should have been.
Yeah, my colleague is talking about problems with PR, etc., which is easy to say afterwards. I mean, this kind of catastrophe, I'm like 40-something, and it didn't happen while I was alive. So this is something we were not prepared for. And one of the critics which I've heard from people after a couple of days was like, yes, but maybe there are some corridors which could have been used during this catastrophe, although there is enough stuff out there that most of it is not useful. Now, not going into atmospheric physics, whether this is possible or not, let's imagine it's possible. Now, if we would have been prepared to it, and if we would have correct models which go directly or indirectly, but which are fed then to the aviation authorities in real time, so that they can actually fly their airplanes, let's say, by wire, right? So that they can make their way through this kind of holes if they exist. Well, maybe this would have been possible. But since this is something which did not happen for at least last 50 years, and before that we didn't have kind of equipment, nobody has this kind of equipment. Now, if you tell me that this will happen every year from now on, probably then we will start making a project which will allow us within a couple of years to actually do this, if it's physically at least useful. But expecting just from yesterday to tomorrow to enable this kind of stuff is just not possible. Because even if we would be able to make the models, there would be no way to directly feed it today to the aviation. So I have no vested interest either in satellites nor in aviation. I don't even have any kind of Lufthansa actions. But I would say that the way the authorities have reacted to this was really more than reasonable.
And if I might add one thing, it was actually done that way. The main problem was that during about 5 days, Europe was just covered. There wasn't a corridor. During one day, there was a corridor up into northern Sweden, and they opened for the first time the northern Sweden airport of Kiruna for a transatlantic flight from New York. And they landed there, and the people continued by train. There exists one train, takes a day. So it was done, and that corridor was open actually for about, I think, 6-7 hours, according to the models, and it was used for 1 or 2 planes. And unfortunately, then this corridor was gone. It opened sometimes later for southern Sweden, was opened there, and then it was open for a couple of hours or half a day in Western Finland, in 30% of the airports, and so on and so on. So it really went on a 4-hour level that certain airports were opened, certain kept closed, and so on and so on. So, though mainly we are not really yet prepared for that, as you pointed out, but what could be done and could have been done with enough safety margins actually was done. In my opinion, at least, as far as I could monitor that from inside our institute.
All right, no more questions. Then I think this was it. Everyone, thank you very much for your time.
Thank you.
Thank you for your time.